All right, the final little section of this chapter, chapter 11, that we're concerned with is 11.5. And it's sort of one of the most super important devices that comes out of, this time period of the 7th century, or at least our understanding of it. And it's the simple pendulum. I'm not sure if I can back that up, that this is one of the most important things, but we're going for it. So we're going to talk about the simple pendulum, and that's just where you have a string or a rope and you have a mass hanging from it, and it swings back and forth. Forms a simple mechanism for some of the earliest clocks that were made. So you have some ceiling support, some cord, a mass at the end, and you know an awful lot from taking 131 about this little system. For one thing, we know that this thing is going to just swing back and forth, always maintaining its distance from that connection point. We're going to say that that distance is L. At any given instant in time, the angle that that cord is going to make from the vertical is phi. And if I look at that little mass, then I can see that there's some forces operating on it. One of those forces is going to be gravity pulling downward, mg here like that. And there's going to be a tension along the line of that cord back towards that connection point. So I have a tension T there. And actually, it's sort of anticlimactic. That's it. That's all the forces I have operating on this thing. When I look at these forces and I have that mg, notice that it's going to have a component along the direction of the tension or along the direction of that cord. And I can convince myself that the angle that that component of the force makes along the along T is at the same angle phi with that line that the cord is with the vertical. And this little component here is going to be mg cosine phi. Then I'm going to have this component of the force that's tangential to, or at right angles to that cord connecting it, or tangential to T. And this component here, this component of the force is a restoring force, because you can see that when this mass is here, displaced at an angle phi, this component of the force that's tangential to that circle that it traces out, that's trying to get it back towards the bottom position where it kind of wants to be. And this component is just going to be mg times sine of phi. And you can go through this diagram and convince yourself that, you have this little right triangle formed here. And so this vector that I've drawn, this restoring force, is going to be the opposite side of this triangle formed here. Anyway, the point is that I have this restoring force that's equal to mg times sine of phi. And so I'm just going to write that here and say F equals minus mg sine phi. I'm writing a minus sign there, so I'm arbitrarily deciding that, hey, this is going to be like my positive x direction. There's a lot of hand waving going on here. You're going to want to look in the book if you want to see this written out in more detail. Now, if I perturb that pendulum just a little bit, just ever so slightly from the vertical, that is, I have this weight hanging from a cord, and I only pull it slightly to the side, like this, well, then it'll just swing back and forth, slowly back and forth, if the cord is long enough. And that motion, I will observe it to be simple harmonic motion. The thing is that perturbing angle phi, that initial angle that I pull it out at the initial distance, has to be small. If I pull it out too far, it's not perfect simple harmonic motion. Anyway, here's a factoid that comes into play about the sine function, and that is sine phi is about equal to phi for small phi. And this only works when we measure phi in radians. So what we're going to say is, and like I said, you don't have to know that. You're never going to be expected to go through this derivation and derive it yourself. But I just want to talk about it a little bit because it is so important from a historical context, and in physics is an important treatment and study. So For small phi, sine phi is about phi. And if I look at this distance that I've been displaced to the side, and I call this little distance x, and I know that L is the length of that chord, phi is going to be approximately equal. And that little squiggly line, instead of drawing an equal sign, I'm going to say it's about, like it's really close to being x over L. Now, with these little factoids, for small perturbations, sine phi is about phi, and phi is about x over L. It allows me to write this restoring force as x equals minus mg. Instead of sine phi, I write phi, and instead of phi, I'm going to write x over L, like that. And remember, this is going to be equal to mass times acceleration in my x direction. So let's just isolate x now from that and say, hey, the mass is canceled out on each side, so the acceleration is equal to minus gx over L. And what we'll notice is, I'm going to have to go to a new page to complete this treatment. Ax equals minus g over L times x, or that acceleration, that restoring acceleration, is proportional to the displacement. And that is a condition which your book will talk about as specifying simple harmonic motion. Remember from the last treatment where we looked at a particle on a turntable, what we found was for simple harmonic motion, A sub x equals minus omega squared times x, like that. So that when I compare these two expressions, I have this omega squared here, comparing it to g over L here, and that is the whole payoff for going through this treatment, is that I can figure out the angular frequency of this pendulum as it oscillates back and forth in terms of g, the acceleration of gravity at Earth's surface, and the length of that pendulum. So let me rewrite that here as omega squared equals g over L, or omega equals the square root of g over L. If I draw this pendulum out again, well, that's phi, and this thing just sort of swings back and forth. Well, remember, f, my real frequency, is just equal to omega over 2 pi. So I can plug that in and get 1 over 2 pi times the square root of g over L, like that. And most importantly, the period is equal to 1 over f, so that's just 2 pi times the square root of L over g. What that tells you is, remember, this pendulum has a length L. Well, one important thing to notice about that period is that it's independent of mass. The mass didn't matter. You could have a small mass or a large mass. As long as your perturbation is kind of small and the string is very, very light, this is going to give you, well, let me just write independent of mass. But anyway, you're given, this gives you the period of a pendulum, and you know g is equal to 9.8 meters per second squared. If you decided, hey, I'm on a desert island and I magically have a ruler and maybe a calculator, but I don't have a clock of any kind, and I had some string and a coconut, say, I could make a pendulum out of that mass, you know, something heavy to attach the end of that string and let it swing back and forth. And if I wanted the period of that pendulum to be 1 second, say, because I was trying to make a simple clock, I could use this formula to calculate what L needed to be in order for the period to be 1 second. And also, there's another thing you could do when I look at this expression. Let's say you had a clock and a string. Well, you have a stopwatch, say, or a watch, and a string and a mass. You use your string and your mass to make a simple pendulum. You measure out the length of the pendulum. Then you go and you measure the period. In this equation, the only unknown, or the only remaining quantity in there, is g. So this is the first method by which we were able to measure g accurately. You construct a simple pendulum, you measure its period and the length of the pendulum, and from this expression, you isolate g. So you square each side, and what you're going to find out, I'll just skip over doing the actual algebra, you find 4 pi squared L over T squared like this. So this is a great way to measure G using a pendulum. And it's funny, we use 9.8 meters per second squared in this class for that acceleration of gravity at Earth's surface. And I've used a simple brass bob on a string that was maybe a meter long. And I've used that just on my own and measured G and got something like 9.76 or 9.72. So it's really, I believe it's it's pretty accurate for measuring that value of G. It isn't so accurate that you want to use it for, you know, a real scientific application, but it's close enough to be slightly impressive. And that ends all the material that you need from chapter 11, and that will cover